Oops. Что это? Можно, да? Курсов 4.
Okay, let us begin our morning session. And our first speaker is Dmitri Bykov, Sigma models as Gross-Neveu models.
Okay, I think it works now. Yeah. So thanks for the introduction. And yeah, so first of all, it's a pleasure for me to give a talk at this honorable meeting. And I'd like to thank the organizers for the invitation to give the talk. And of course, I'm happy to congratulate Nikita Slavnov and Lena Chekhov on the occasion of their birthdays. And I will be talking about some aspects of integrability, which I think both of them have had and are still have interest in. I think the switch still is not working, so can you please turn it on? Oh, okay, I'll comment on this slide for the moment. So yeah, it's based on some of my work that I did in the past couple of years. And it's actually some kind of, well, I'm going to be talking about the equivalence between a class of sigma models and a class of generalized Gross-Neveu models. And I think this equivalence kind of sets up a research program of sorts. So it's maybe only at the start of this research program. We're now at the start of this research program. And yeah, it's based on various papers. So in particular, we wrote a big review paper with Ian Affleck and his students, because there's another part of the story that has to do with spin chains and some phases in condensed matter physics. That's mainly related to flag manifolds and SUN spin chains and flag manifolds that appear, flag manifold sigma models that appear in continuum limits of those spin chains. So yeah, it's actually an interesting story in the sense that in condensed matter physics, most of the spin chains that are actually of interest, or generic spin chains, they're not integrable, and their structure is very different from the structure of integrable models. In particular, they can be gapped and not gapless. And the integrable models are some special points in that space. But anyway, today I'll talk mostly about another part of the story. So this equivalence between sigma models and Gross-Neveu models, like I already mentioned. And so first, a brief outline of the talk. So there is a wide class of integrable sigma models that are exactly and explicitly equivalent to mixed bosonic and fermionic Gross-Neveu models. I will review what these are. And the idea is that sigma models are pretty complicated objects. So although they are kind of generalizations, straightforward generalizations of quantum mechanics, but still they're very complicated. And Gross-Neveu models are also two-dimensional models, but much simpler ones. And there are lots of tools to kind of solve them and so on and study them. Besides, there are many actually enhancements that you can do to these models when they are formulated in this Gross-Neveu form. So for example, one can construct deformations, easily construct deformations of those models, trigonometric and principal also elliptic deformations. You can prove normalizability at one loop at least, or probably in many more loops, but so far it has been done at one loop. So the fact that the deformed models should be normalizable, it's not obvious. But here it can be done very easily. The proof can be done very easily. Besides, one can consider those theories actually on general Riemann surfaces. So not necessarily on a plane with decay boundary conditions, but some more general Riemann surfaces. Again, has not been done much, but there is lots of potential in that direction, I think. So one direct consequence of the fact that sigma models should be equivalent to Gross-Neveu models is that sigma models are actually models with polynomial interactions. So that's unusual because we typically expect them to be the interactions to be given by some infinite series. When you expand around some point in target space, you get an infinite series and so on. So here somehow the infinite series disappears, or you can have some constraints that can be solved by an infinite series. So here there are no hidden constraints. Everything can be solved explicitly. It's all polynomial. So it gives a new method for constructing supersymmetric theories, and in general gives a new look at theories with fermions. So theories with fermions are inevitable here, so they're needed for integrability. So you cannot consider pure bosonic models. And besides, among the theories with fermions, there are of course many of them, but in particular supersymmetric models can be constructed in a new way that I'll explain briefly. Then there is a general class of models that can be characterized as models with quiver variety phase spaces. And yeah, like I already mentioned, perhaps these models can be put on Riemann surfaces in an integrable way. So here's some key example, which is the map between the CPN model and the Gross-Neveu model. So that's a key example. So basically, you just need to understand this example, and then the rest is kind of a generalization. Let's start. So here is a Lagrangian of a Gross-Neveu model, as known since the 70s. So there is some kinetic part and the quartic interaction. But here, unlike the original model considered in the 70s, the main field psi is actually a boson. So it's Dirac spinor. So we could call it a Dirac boson here. So you see this spinor splits into two wild components, U and V. And then if you rewrite the Lagrangian in those components, it just becomes this thing here. And now a simple, you can see that basically V, either U or V, they enter algebraically. So you can just eliminate either U or V. They enter symmetrically. It doesn't matter which one you eliminate. So you just eliminate V and you get this Lagrangian, which is actually a CPN model in gauge linear sigma model approach. So gauged means there is actually a gauge field. There is a gauge field standing here in the covariant derivative. It's a U1 or rather C star covariant derivative. And to see the equivalence with the usual formulation of the CPN model, you should set a partial gauge, which is U bar U equals 1. One could call it Hopf gauge because it exhibits the Hopf vibration and so on. So it's a partial gauge for the C star gauge symmetry. So in usual formulations, they start from unitary gauge groups like U1, and U bar U equals 1 is already assumed from the start. So here the point is that we relax this condition, and that's precisely what leads to this Gross-Neveu framework. So in principle, like I say, it's a direct map. You just exclude by means of equation of motion, yeah, one of the variables, V or U. I mean, there, of course, each of these is an n-dimensional vector, yeah, you exclude them, you get this Lagrangian. Then you set U bar U equals 1, and then you get the Lagrangian of the standard CPN model. Yeah. No. It's a commutative variable. Yes, a Dirac boson. Okay. Yeah. Yes, sure. Yes, I mean it's a generalized Gross-Neveu model. Yes, I mean in general you will need to have both bosonic and fermionic variables. So, for example, I will claim that in the supersymmetric model, actually bosons and fermions enter symmetrically. So it's a combination of fermionic and bosonic Gross-Neveu model. That's right. So here, one key point. So like I said, the gauge symmetry here is C star. So the key point is that here we're working only in Euclidean signature. So the worldsheet is a Riemann surface. In general, you can consider R2 or something, but the point is that in Euclidean signature, chiral symmetry is a complexification of the original symmetry. So if you have U1, chiral symmetry will be C star. That's unlike in Minkowski signature, where that would be U1 times U1. And that's the symmetry we are gauging, actually. The gauge field in the CPN model gauges that chiral symmetry. So it will be important that there are no anomalies in those symmetries, because these are true quantum gauge symmetries. Yeah. So for example, in our example, the chiral symmetry acts as multiplication of U and V by inverse powers of complex numbers, non-zero complex numbers. So if lambda were a phase, this would be the usual U1 charge symmetry, as in electrodynamics. But here it's a complex number. So in particular, what does chiral symmetry exclude? It excludes interactions of the type U to the 4 and V to the 4. Yeah. So the usual Gross-Neveu model, non-chiral one, it allows interactions U to the 4th and V to the 4th. The chiral one just says you should have U squared, V squared, and that's exactly what we have in the previous slide. So actually, it was already observed in the 70s that even in the fermionic Gross-Neveu model, if you build bilinears in the fermions, they satisfy some classically integrable equations of motion. I will explain that these are actually moment maps or currents in the physics interpretation, these quadratic guys. Here, they will be quadratic both in bosonic variables. Well, there will be a term quadratic in bosonic variables and a term quadratic in the fermionic variables. So here's the first application of that model. I'm just showing you a quantum mechanics application just to show that that reformulation is actually very useful. So even in quantum mechanics, it's like if you want to consider some kind of generalized spherical harmonics, here I built that. So we want to consider eigenfunctions of the Laplacian on CPN, right? That's what quantum mechanics is about in this case. So we replace ZZ bar variables by T, and then we see this is just a first order formulation, and this is the Hamiltonian, right? So now the quantization gives that U and V commute to the delta function. So V is a derivative with respect to U. So the Hamiltonian, which is just this thing here, it becomes this guy here. Plus, we have an extra constraint, which we get by taking variation with respect to the gauge field, right? So there is a gauge field here. So varying with respect to the gauge field gives U times V equals 0, or U bar, V bar equals 0. And upon quantization, that gives constraints on that the wave function should be homogeneous, right? There is an Euler vector field. So basically, you have a homogeneous wave function with this Hamiltonian acting on it. You can easily write out its eigenfunctions as generalizations of well, some polynomials, yeah? The arbitrary wave function, this just gives rise to the multiplicity of the
Dmitri, is there an ordering problem in this?
The spectrum. So this is, I believe, by far the easiest way to compute the eigenfunctions of the Laplacian on CPN. Okay, so now I'll pass over. I'll explain that it's also easily possible to construct deformations of those theories. So we consider again, the Gross-Neveu Lagrangian with that bosonic variable and so on. And in place of the single coupling constant kappa, we place a classical R matrix here. Yeah. And then, well, there is another current. So the undeformed model was invariant with respect to SUN. So there was another conserved Noether current. Here, it rather satisfies a deformed version, the conservation condition and so on, and a flatness condition. So if R were 1, this would just be the equation of motion of the principal chiral model, which again hints at the integrability of where integrability comes from. As usual, we want to have a Lux connection representation for our equations of motion. So the Lux connection has this simple form. So there's an R matrix acting on this current, J. And by the way, this current is bilinear in these U and V variables. So the current is basically U times V. So we have this connection, and its flatness gives us the classical Young-Baxter equation for R. So yeah, the models can be easily deformed in such a way that the Lux formulation persists. And you see this connection. So here maybe I should comment that, well, U is a spectral parameter and S is the deformation parameter. Yeah. So here in the Lagrangian, one finds Rs, which is the classical R matrix with parameter S. So S is the deformation parameter. And here it stands here, but U is a spectral parameter in the Lux connection. Yeah. Yeah, you could put, well, the case that has been most studied is the trigonometric case, where you put a trigonometric R matrix. You could as well, in principle, have an elliptic one. Okay, so here is some simple calculation in the trigonometric case. So we want to prove renormalizability, so that the form of the Lagrangian persists at one loop at least. Presumably, it can be, like I said, proven at higher loops as well. So here are the Feynman rules. They're very simple, right? We have a Green's functions, which are like the Green's functions of the fermion, although these are bosonic fields. And there is a vertex, which is given by the R matrix. And at one loop, the divergences are just given by these two diagrams. So you just, there's an R matrix at each node, and you sum and so on. And you want to find a solution to the equation, to the renormalization group equation. That's the derivative of R is a beta function given here. And you usually find that the solution is that S is the exponent of n tau. So S is the deformation parameter. That's what's running. That's the coupling constant. Yeah, the deformation parameter is the coupling constant. Tau is the RG time. So it's log mu in physics notation, logarithm of the energy scale. And n is the dimension of the ambient space, so CPN minus 1. And in fact, it will be the same exponent for all Grassmannians with the same symmetry group. So for SUN, the solution will be the same, actually. So that's a proof that the model is renormalizable at one loop. And yeah, so as you can see, you don't need to use any complicated methods like the background field method here. It's just given by these two elementary diagrams. So a simplest example is the sausage model, so which corresponds to the case n equals to 2. So the deformed metric in this case has the following form. So you can get this metric by plugging in the classical trigonometric R matrix in that Lagrangian, integrating out V, like I said before, and then you get a geometric formulation of the sigma model with a metric, in general metric, B field and dilaton. Well, it's called the sausage model because the target space looks like a sausage in some regimes. In particular, in the UV, it becomes an infinitely long sausage. So it's kind of a flat, like a cylinder, a flat cylinder. So that's the interpretation of that is that this is asymptotic freedom. So flat free theory in the UV, and in the IR you get a collapsing sphere. Basically, collapsing means that the coupling constant grows. And the same construction can be applied to CPN minus 1. In this case, you have a generalized cylinder, C star to the n minus 1 in the UV, and then CPN minus 1. So it's what's called an ancient solution of the RG flow. But here, we already proved it just by this algebraic calculation. Okay, so if you want to go back to the geometric form of the model, it's going to be pretty complicated. Yeah, so if you integrate out V and you go back to the metric, B field and dilaton, those are going to be complicated functions in general. And in that case, we know what the beta functions of the sigma model are, and we can compute the RG flow or generalized Ricci flow by solving these equations. But that, of course, has to map or be consistent with that simple calculation from before. So as you see, we have very complicated equations, but yes, it has been checked in some low dimensional examples that it works, that actually they're satisfied just by that simple solution that S is equal to exponent of n tau. Basically, just that simple solution translates into a very complicated geometry once you integrate out the V variables with a metric B field and dilaton that satisfies this complicated RG flow equation. Okay, so now I'll explain why one actually needs fermions in this model. So having fermions is actually inevitable because purely bosonic models are affected by chiral anomalies. So like I said, in these models, we're actually gauging chiral symmetry. So for example, in CPN, what is the traditional definition of CPN minus 1, right? It's Cn modulo C star, or Cn minus 0 modulo C star. So C star is the gauge symmetry in question. That's the same gauge symmetry here. That's the chiral symmetry of the Gross-Neveu model. And we're gauging it. So we need to make sure that it's free of anomalies. But the purely bosonic model will have anomalies because it's has been known since the 60s that there is a effective action is not gauge invariant. What I mean by not gauge invariant, I mean that it's gauge invariant with respect to usual gauge transformations, but not with respect to the complexified gauge transformations, which are the chiral gauge transformations. Yes. So usual gauge transformations are when the gauge parameter is real. So alpha equals alpha bar. Then this thing is invariant. But if alpha is actually complex, then it's not invariant. That means that in quantum theory, there is an anomaly. This is not a true gauge symmetry. So you cannot really use it as a gauge symmetry. So you have to do something about it. But luckily, because the model is formulated in such a way that in first order form, so that the bosonic field actually looks like a fermionic field, like a Dirac boson, like I said. An easy way to cancel the anomaly is just to add the same fermionic piece symmetrically. And then, well, the effective action comes from the determinants of these operators. So these determinants just cancel. You have a 0. So you basically have a coefficient n minus n 0 here. The anomaly is canceled. So that's one way of canceling the anomaly. You could as well introduce interactions for the fermionic terms. So the anomaly comes purely from the kinetic piece. So the interactions do not affect the anomaly because it's a one loop thing. Okay, so here's a general setup. So the CPN model is a main example, but you can easily guess what the generalization should be. So recall the CPN model once again. So here you have this kinetic piece. So it could be viewed as a Poincare-Liouville one form, like PDQ one form, corresponding to a complex symplectic form dVi dUi, right? And then there's an interaction term. So the question is how to generalize this thing. And there's also a gauge field, right? So the point is that, well, the first thing to notice is that the gauge field actually performs complex symplectic reduction. So when you take variation with respect to the gauge field, you get a moment map equals to 0 equation. That's a general property of such kinetic terms that look like Poincare-Liouville one forms. That would be also true in mechanics. So the gauge field performs complex symplectic reduction. Then what can we do? We could have a general complex symplectic quiver supervariety, phi, which is the phase space. Yeah. So in the CPN case, the symplectic variety is T star of CPN minus 1. That's the relevant symplectic variety. Supervariety means that we add fermions, so there's some supersymmetrization of that thing. Then in this quiver supervariety, we have arrows going from one node to another node and back. And those arrows are precisely in one-to-one correspondence with these U and V fields, which are nicely packed into these Dirac spinors. Yeah, so the matter fields are in representations U plus V, in representations W plus W dual, and they correspond to U and V fields. So they're dual representations. These are arrows going in opposite directions. And you need that to be able to pair them in the kinetic term. And then you have a complex gauge supergroup G gauge. You also have complex, typically you will also have complex global symmetry group. So these quiver varieties, they typically have some global symmetry. There are some, besides gauge nodes, there are some global nodes. And there will be some global symmetry group with respect to which you can build a corresponding moment map that will be called J. Well, in math literature, people usually call it mu, but J is meant to remind that it's actually a current in physics notation. That's precisely part of that Noether current that I mentioned before. Or in other words, it's a chiral Wezumino kind of current, Kac-Moody current. In these models that I mentioned, J is just U times V. So it's a matrix, U direct product V. It contains no derivatives. That's the benefit of this formulation. Okay, and then the Lagrangian is you pair these fields. So now V and U can be arbitrary representations of those groups at the nodes and so on. Yeah, you pair them. And then the interaction is a pairing of the two moment maps, J, J bar. That's the general form of the interaction that you can write for this general setup, this complex symplectic super variety. So like I mentioned, yes, in the CPN example, J is just U times V. And then this becomes this U bar, V bar interaction. Kappa is a complete constant. Again, you could introduce deformations and so on. Now, an important thing is this chiral anomaly cancellation condition, like I said. It's actually a Wesermann-Witten anomaly cancellation condition, and it takes the form that the super trace of the gauge generators, squares of gauge generators should be 0. Well, Ta, Tb should be 0. Super trace with respect to this representation where the matter fields sit. The fact that it's quadratic, that's because it comes from diagrams of this form. That's always the case in 2 dimensions. So in 4 dimensions, you have triangle diagrams. In 2 dimensions, you have these diagrams with two angles. So this is just a generalization of the usual Wesermann-Witten anomaly cancellation conditions to the case of Euclidean worldsheets. So in Euclidean worldsheets, you have to a little bit rethink the whole theory of Wesermann-Witten models. And here, the relevant conservation condition is this: the super trace of 2 generators is 0. So it's also conjecture that it's actually a sufficient condition for the cancellation of the anomalies in integrability-related charges. So it has been known since the 80s that in models like the CPN model, there are some anomalies in integrability-related charges, which are called the Lusher non-local charge and so on. So there was some extremely lengthy calculation showing there is some anomaly. So the charge is not conserved because of some OPE of some currents and so on. But the non-conservation was, yeah. So the conjecture is that this can be avoided once the chiral anomaly cancellation is satisfied. And that's also has been known that if you add fermions to the models in various ways, you can cancel this anomaly, these anomalies. We're having some light show, yeah. But I'm saying there was no conceptual understanding why these anomalies arise or why they are canceled by fermions. So conjecturally, it's possible to show that it's directly related to the chiral anomalies. Okay, so now I'll show some concrete example. So the CPN models with fermions. So like I said, the complex variety, symplectic variety, we need a complex symplectic form, yeah? So we take T star of CPN -1, for example, yeah? That's a hyperkähler variety, so in particular, it has a complex symplectic form. Here we take a fermionic completion, which is CPN -1/n. And the gauge group is C star. So you take n bosonic variables and fermionic variables, and they're charged in the same way with respect to the gauge group C star. Yes, that's what gives you CPN -1/n. That can be also thought of as a fermionic conifold bundle, O1 plus O1, etc., where the fibers are fermionic. That's a useful way of thinking about it because there are other, in all examples, fermions live in some bundle over CPN -1 or over the base. Then what we need to do to construct the corresponding integrable model, we have to choose this global symmetry that gives rise to the moment map, which enters in the interactions, right? You could pick this global symmetry in different ways. You could pick, say, an empty trivial group of 1 element, then the moment map is 0, then you have no interactions. And there are many ways. So for example, I can pick G global as SLN times 1 embedded in PSLN/n. So PSLN/n is the symmetry of the kinetic piece without the interactions. If I pick this, I write the corresponding moment map. I write the Lagrangian, yeah. Then I get what is called minimally coupled fermions. Now, if I take G global equals to the full group PSLN/n, then I get a CPN -1/n sigma model. So sigma model with a target space supersymmetry. It's related to twistor string theory and so on. Has been investigated in many papers. So these are at least 2 possibilities. Okay, the most kind of involved possibility, maybe most interesting one, is the supersymmetric model. So you may ask, how can we get a supersymmetric CPN model out of this construction? And I mean supersymmetric. By supersymmetric, I mean supersymmetric on the worldsheet. So not target space supersymmetric, but the usual worldsheet supersymmetry. And that's possible. But here, as opposed to the usual formulations with superspace, this relies only on target space supersymmetry. So you start with target space supersymmetry, then you gauge part of it, and then you get worldsheet supersymmetry. That's the logic. The gauging is more involved. So you take here the phase space will be T star of the fermionic tangent bundle to CPN -1. So as opposed to the minimal fermions case where we had a conifold bundle or 1 plus a 1 plus a 1, etc. Here we have a tangent bundle, and a geometric way of constructing this tangent bundle is by action of this triangular group, subgroup of SL1/1. So it's a two-dimensional complex group where lambda lives in C star as before, but then we have an additional fermionic gauging. There's an additional one-dimensional fermionic gauge group. So it's a supersymplectic reduction. It's a enormous supersymplectic reduction in the sense that it's not just purely a bosonic symplectic reduction. Well, it can be described explicitly. So you start with Cn/n. You introduce coordinates, this u and c coordinates, and the dual v and b coordinates. So here u and v, u straight and v straight are just the original u and v variables, and b and c are the fermionic variables. And we write the Lagrangian. So that's the free piece. Yeah, we write this curly v and u with covariant derivatives acting in this triangular form. So a bar and correspondingly a are the components of the C star gauge field as before, but now we have an additional fermionic gauge field called W bar. And then you can already at the level of this free Lagrangian, you can check that it's invariant with respect to worldsheet supersymmetry transformations. So it was I think in ungauged form, so just without the gauge fields, it was observed some time ago. It's actually invariant with respect to this worldsheet supersymmetry transformations. But to incorporate the covariant derivatives, you actually have to also include the fermionic gauge field. And to write the interactions, we take G global equals SLN diagonally embedded in SLN/n. So the moment map is this: u times v minus c times b. So u and v are bosonic variables, and c and b are fermionic variables. Okay, that's the key points. Then we write the interaction term as trace of jj bar. And then that's all equivalent to the usual supersymmetric CPN model. Here I explain how the equivalence is established. So we write the Lagrangian, and then we pass to a gauge. We pass to the usual gauge that's usually imposed. So the usual gauge is u bar u equals 1, the Hopf gauge. So, and then an additional gauge u bar, scalar product of u bar u and c is 0. So the scalar product of one bosonic variable and one fermionic variable is 0. That's a gauge. That's a gauge fixing for the fermionic gauge symmetry. That's this W bar gauge field. So we gauge field fix in this way. Then we eliminate the V and V bar fields, and then we obtain the usual supersymmetric CPN model. So it has been known for a very long time that the supersymmetric CPN model involves coupling a bosonic CPN model to a chiral Gross-Neveu model. So the point here is that the bosonic piece of the model is a chiral Gross-Neveu model in itself. So it's all can be written in a much more symmetric form. So there, instead of dealing with this Lagrangian, it's much better to deal with the Lagrangian from the previous slide. That's the claim. Okay, so there are many open possibilities that this related to this. So first of all, models of this type, like CFT deformed by JJ bar perturbations, have been investigated in many works, I think by Zamolodchikov and so on, many people. And in particular, there is actually a conjecture for an all-loop beta function for such models. So in particular, there is a conjecture also for deformed models. So when this D is a matrix of coupling constants here, but if D is proportional to the unity matrix, then the beta function is just this simple function here. So C2 is the Casimir of the symmetry group. So in the case of SUN, it's just N. And then there is this denominator, which involves the level of the Kac-Moody algebra. So it's assumed that the CFT has a Kac-Moody symmetry, and we're deforming by the Kac-Moody currents, the product of Kac-Moody currents. This here. But in the supersymmetric case, the level is actually 0. That's extremely level of Kac-Moody algebra. Yeah. So it's extremely elementary to see that the level is 0 because the level is just a correlation function given by the correlation function of J and J. And it's just 0 because the U and V contribution cancels exactly against the C and B contribution. And that's completely, so in that case, it means that the beta function is one loop exact. So you see the series terminates at kappa squared. And that's compatible, that's known for the CPN, supersymmetric CPN model, has been known for a long time. It can be derived in various ways. So that's correct, at least in this case. But of course, if it's also true for non-zero levels, if this beta function, so it's kind of a conjecture, a long-standing conjecture. But I mean, if it's true, that gives a beta function, exact beta function for a really wide class of sigma models, including CPN models with various couplings of fermions, Grassmannian models, flag models, lots of stuff. So just for your comparison, typically beta functions are very complicated. So for example, at 4 loops, they involve some zeta of 3. We heard some zeta of 3 yesterday. So this is quite extraordinary that it could be exact. Then I want to point out that this whole thing can be coupled to worldsheet metrics, so it can be placed on Riemann surfaces. In that case, you have to assume that U and V are sections of some bundles. So some line bundle L and V is a section of canonical bundle times L minus 1. And then you have a mixed gauge gravitational anomaly cancellation condition. It comes from this diagram where you have a gauge field and a metric on the other line. It's again quadratic or bilinear. The point is that for most models, say for the supersymmetric models, or well, for models with one, well, yeah, okay, let's say just for most interesting models, the super trace of the gauge generators is 0. And then one way of satisfying this condition, or in some cases, the unique way, is to say that J is proportional to the identity matrix. And that means that the gravitational couplings of bosons and fermions are the same. And that's what is called A-type topological twist. So that's another way of obtaining twisted models, just from the condition of cancellation of chiral anomalies in the presence of a background gauge field, background metric. So the whole setup can be generalized to Riemann surfaces. So one funny thing is actually in these models, at least on R2, you can actually pick a gauge where the gauge field is 0 completely. That's completely different from typical models. You can completely eliminate the gauge field by an explicitly solving the equation for the gauge transformation. So this is a gauge field analog of conformal gauge in string theory. So that's a gauge analog of in string theory, you can eliminate the worldsheet metric. Here, you can basically eliminate the gauge field. But on Riemann surfaces, you can eliminate the gauge field almost completely up to moduli. Then you have to integrate over moduli of holomorphic gauge bundles. That's the same as integrated by this theorem of Narasimhan and Seshadri and so on, Atiyah Bot and so on. That's the same as integrating over representations, projective representations of the fundamental group given by this equation. So that's kind of an interesting theory. Like in string theory, you integrate over moduli spaces of complex structures. Here, you could be integrating over moduli spaces of holomorphic bundles. Again, it's interesting whether integrability can be preserved while doing that. Okay, and so that's the final slide. So the point of my talk is that, or the main result is that there is an exact equivalence between sigma models, special sigma models with complex target spaces like CPN and chiral Gross-Neveu models. So for example, in this way, it naturally explains why there are integrable models with flag variety target spaces, because there is a complex symplectic form on cotangent model to the flag, Nakajima variety, and so on. So, but there are many, so the models have polynomial interactions, which is unusual for sigma models, like I say. They have ultra-local Lux pairs. The Lux pairs that you get are natural generalizations of the ultra-local Lux pairs, first constructed by Butsko for the sphere model. And there's also Lukyanov and others for the deformed sphere model. So this is a natural generalization. Then perhaps it's possible to compute the all-loop beta functions. Then one can place the sigma models on Riemann surfaces in a natural way. And I should also point, there's a very funny connection that actually there are 4-dimensional reductions of 4-dimensional gravity to 2 dimensions also gives rise to sigma models with complex target spaces. So not arbitrary target spaces, but complex target spaces. And the conjecture is that these U and V variables are the dimensional reductions of the Ashtaker variables in this. So Ashtaker variables are known to have local Poisson brackets, and besides, they're known to make interactions polynomial in gravity. So that should be a counterpart of having these polynomial interactions in sigma models. And so hopefully this can give rise to a full quantum theory of sigma models. So because I think this framework is the best one for, or appropriate one for quantizing these theories. I mentioned some one loop results, but many of these things presumably can be extended to the full theory. Thanks.
Questions? So I have a small question. For example, just to clarify what kind of models you are dealing with, maybe can we consider, you are studying field theories, and even more, you are studying quantum field theories. And let us simplify it as much as possible. Consider trivial reduction when, in classical case, when your field theory is reduced to classical mechanics. So all fields are independent of space field variable. Then you should get some classical mechanical integrable systems, maybe of Gaden type or integrable tops or something like that. Do you know what kind of models?
Yeah, I mean, I'm pretty sure that these models are related, closely related to Godin models in general, but I think that's when you involve more couplings. You could consider couplings not just mu mu bar, but you can consider couplings of several moment maps. I think that's where you would get some Godin models. But in the simplest examples, of course, you just have reductions of homogeneous space. You have geodesics on homogeneous spaces, right?
So these are integrable tops and the Godin extensions. Is it correct?
I think so. Yeah, roughly speaking, yes. Yeah.
Okay, thanks. More questions? Okay, let us thank speaker again.